Hello and welcome back to our video series on PoliteGuard, Intel's latest natural language model. I'm Ehssan Khan, a senior AI software solutions engineer, and this is the third video in the series, where we'll dive into the fine-tuning process for text classification. The first two videos introduced PoliteGuard and discussed synthetic data, its benefits, and limitations. If you haven't checked them out already, there are links in the description. The idea of fine-tuning in natural language processing was borrowed from computer vision. The computer vision models were trained on large datasets, such as ImageNet, to teach them basic image features, such as colors or edges. These pre-trained models were then fine-tuned on a downstream task, such as classification of berries or flowers, on a relatively small, labeled dataset. The key observation was that these fine-tuned models would perform significantly better compared to the models that were trained from scratch on the same amount of data. Despite the popularity and success of this transfer learning method in computer vision, for many years it wasn't clear what the analogous process would be for natural languages. So how does fine-tuning compare to pre-training for natural languages, you might ask? With pre-training, language models gain a general understanding of languages and language patterns, but they're typically not capable of following instructions or answering questions. Fine-tuning continues training of a pre-trained language model to improve its performance on specific tasks. For instance, PoliteGuard was fine-tuned from BERT on synthetic data of customer service interactions to classify text into 4 categories of polite, somewhat polite, neutral, and impolite. With fine-tuning, you can improve the performance, reliability, and privacy of your language model while reducing the associated costs compared to subscription-based services. Let's take a closer look at the fine-tuning mechanism. First, we start with the transformer block. Then, we add a classification head on top of it. We fine-tune the model by looping through the training dataset a few times in order to minimize the loss function without overfitting data. Here is what's happening under the hood. A special classification token, CLS, is typically added to the beginning of input sequences for transformer-based models such as BERT. During the fine-tuning process, as the CLS goes through the model layers, it becomes increasingly aware of the meaning of the whole sequence, making it a good representation for downstream tasks such as classification. Now that you're familiar with the fine-tuning process, let's wrap up with some practical advice. First, collect real data or generate your own synthetic data. Check out the previous video in the series for synthetic data generation. Then, fine-tune a relatively small language model on your dataset and evaluate its performance on your test set or a benchmark if available for your task. Finally, experiment with increasing the base model size, training dataset size, and if necessary, task complexity. Want to try all of this out in code? We've got you covered. Check out our blog post on fine-tuning for a deeper dive into the topic, with hands-on examples using PyTorch, Hugging Face transformers, and PyTorch Lightning, utilizing Intel Gaudi AI accelerators. Visit the project's GitHub page to download the open source data generator and fine-tuner that you can run on an AI PC or Intel Tiger AI cloud. Thanks for watching, and please stay tuned for our next video series on OPA, where we shall revisit PoliteGuard in the context of guarded language models.